I'd like to talk to you about what we do with the science and the mathematics that we learn about retrofitting your house. So once we know how much earthquake force we're going to resist, we have to figure out, how much hardware and plywood, et cetera, we need to resist that force. So I want to go over the basic theory that we use to determine that. So when we talk about a house being struck by a certain amount of force, we don't actually mean the house is being pushed on. We just do that for conceptual reasons. So what actually happens is the ground moves from underneath the house. So here's an example here. The ground is moving. That red arrow shows ground movement. And then due to inertia, the house wants to remain because the ground is moving underneath it. It leans like this. So that's trying to fall off the foundation like that. Now the other way to look at that is as if the house were being pushed on. So you see how this and this look exactly the same, but in this case the red arrow represents, we call it the force pushing on the house, even though it's not technically pushing on it. From a conceptual point of view, in order to understand and do our design work, that's how we refer to it. So now I'd like to show you a little bit about the rationale of using the different components. Every component of a retrofit, the bolts, the shear transfer ties, the plywood, they are all able to resist a certain amount of force. This force has been determined in laboratories, so it's very accurate. So here, let's just go over a manufacturer's catalog so you can see how these ratings of earthquake force resistance are made. So right here we have a piece of hardware called a GA1. And then if you look, this is the fasteners. They want 4 10-penny nails, 1.5 inches long, so that's the fasteners we use. And then here it's called the load direction. That means that in a direction that resists lateral forces. That's what an earthquake is. So this is the floor load right here. And what that means is if there's a person who weighs 235 pounds and they're standing on top of the GA1 hardware, that the hardware will be just fine. If there's someone who's 400 pounds, it'll start to bend and start to fail. Now when we get over to the earthquake section, you can see how it's higher. It's 330 pounds. The reason for that is the building code says, well, if something's only going to have to resist some force for a short amount of time, it will be able to resist a greater amount of force. So what that means is they took this 235, they multiplied that times 1.6, and they got 330. So every time you look in a hardware manufacturer's catalog and it'll say something can resist, say, 200 pounds, or let's say it can resist 100 pounds, you just multiply that times 1.6, so that from an earthquake point of view, you can say this resists 160 pounds. So when you're designing a retrofit, you always need to keep that in mind. So that's basically how you read these catalogs. So I want to go into, this is from Standard Plan A. So here's the different types of hardware. Even though all these ratings are wrong, which you're going to see if you go to the Standard Plan A video. So for example, it'll have an L70 and it'll say it can resist 458 pounds. So that's 458 pounds of earthquake force. So this L90, it can resist so many pounds of earthquake force. So all these bolts and everything, they're rated in terms of the amount of earthquake force that they can resist. And then the way Standard Plan A put it together, it said, okay, we need to resist so much force based on these engineering calculations that were done as its basis, and therefore we need to just make sure it can resist that much force based on this number. So for example, if Standard Plan A said we need to resist for this house 10,000 pounds of force, we need probably about 12 bolts that can resist 820 pounds per piece, and probably 20 of these H10 hardwares. So we just want to make sure it resists the amount of force that it's supposed to resist. So just to give you an example of this, let's look at bolts. So here we have a 1/2 inch bolt. Then there's a mud sill plate that we put on it. That's a type of washer that's discussed in the cripple wall retrofit video on this website. And they can resist 1,340 pounds of earthquake force. Now if we take a 1/2 inch bolt and we don't put on the mud sill plate, it can resist 1,119 pounds of earthquake force. Now every component in a retrofit, such as the shear transfer ties, the plywood, and the bolts, they all resist a certain amount of force. So when we do a retrofit, after determining how much force the house must resist by using engineering calculations, we just need to put in enough of these components to resist that amount of force, and we're all done with our retrofit. Now we've looked at hardware capacities, but there are also some things that have a capacity which are not rated in a catalog. And for these, you need to calculate the capacities. For example, here's one of the components we use in some retrofits. And as you can see, it'll really depend on how many shear transfer ties we put in, how many bolts we put in, what type of wood this is. And so there is no standard capacity for this. It just depends how you put it together. Here's another type, so it's going to depend on how we nail here, again, how many bolts. And so again, there's no catalog you can look in. You just have to use the engineering principles and figure out how you need to build it to get the capacity that you need. So here's the plywood capacities. This has to do with the way the plywood is nailed. For example, if right here it's nailed with a 10-penny nail, and then the nails are put 2 inches apart on the edges, it can resist 870 pounds of earthquake force. This is just like the way hardware is rated. It's how much force can resist, except with plywood, it has to do with per linear foot of plywood. Here's one here where you can use an 8-penny nail, and if you nail it 4 inches apart on the edges, you'll get 430 pounds. If you nail it 2 inches on the edges, you can get 730 pounds. So that's how that works. And then we have stapled shear walls. These also have an excellent capacity. You need a special type of gun. And there are some things about stapled shear walls that you need to know. I'm not going to go over that right now, but you need to be very, very careful about using these. And I don't recommend an amateur even thinking about using this. These are high capacity shear walls. There were some tests done at the American Plywood Association laboratories. And if these particular walls were put together in a certain way, they had tremendous capacity. However, they had a lot of problems. Again, I'm not going to go over them right now, but it's just interesting to be aware of that. And finally, we have a plywood to plywood connection. This is used very rarely. Sometimes someone will put a piece of plywood up in 2 pieces when it should have been 1 piece, and then we can take a piece of plywood and connect the 2 together. And this is the information that we use for that. Again, everything here has some kind of capacity. A nail has a capacity. Heck, a piece of bubble gum has a capacity. And you just need to know what those capacities are and design your retrofit. I hope the information in this video has helped you understand more about seismic retrofitting and how to protect your own home. We're producing more videos, and if you would like to know when they are available, please click the subscribe button. Thank you.